All right, welcome everyone. Today we're going to be covering big O notation. How exactly big O notation works, how to read logarithms, and how it gets interpreted. So I'm actually going to bring up our curriculum here so that we can take a look at it. This first portion is going to be more of a guided discussion where we talk about things rather than straight going into it within Python. So here's logarithm. So what is big O notation and what is it used for? So big O notation is essentially a mathematical notation for computer science that uses logarithms. And we'll be diving into logarithms here shortly. Now, big O notation essentially just tells us how efficient an algorithm is, whether that's log of n, O of n, log of n squared, so on, right? Essentially, it tells us, hey, is this going to be in linear time? Is this algorithm going to get progressively worse depending on the amount of input? Or is this algorithm actually going to get more, not necessarily faster, but stay consistent in speed regardless of the amount of input? That's kind of where big O notation guides us to. And we'll be looking at the different types of big O notations here shortly. So now, in big O notation, when you're looking at it mathematically, all it means is 2 to the power of something. So for example, in exponential values, we have 2 to the power of 4 would give us 16. Well, when we're using logarithms, log of 16 would give us 4. And same thing with log of 2 would guide us, or excuse me, log of 128 would guide us all the way to 7. Does anyone have any questions about this information, about how this works or how to exchange those in between? Okay, doesn't seem like we have any questions, so we're going to go ahead and move on into um, continuing talking about big O notation. So now logarithms are just inverse operations of exponents, and everything inside of big O notation will always be to the logarithm of 2. All right, so now when it comes to big O and how to establish big O, something that we should always keep in mind is that big O is established by its worst scenario. So we've already covered linear versus binary search. If I were to have a list of numbers that is a list of range between the numbers 1 to 100, and I was looking for the number 100, I would write a for loop, or let's call it a function. Let's call this linear search. And this would essentially say for, should take X and a list for num in list. Then if num is equal to X, I want to return num. And otherwise, or at the end of it, I'll just return none if that never gets triggered. So this is my linear search. Now, when I interpret how quickly this would work, I would interpret it by its very last index. So here's my list of numbers. Go to create a couple boxes here. See something on the chat. I will check it here shortly. Give me a second. All right, checking the chat now. Oh, thank you, Kenny. Appreciate you sharing that. All right. So now this is how the list of numbers is looking at. If the number I am looking for, in this case, if I was looking for number 1, well, one could potentially make the argument that this is actually O of n, meaning there's no search time. It's an instant time because in the very first index, it's going to return the very first number. All right. So one could make that argument of saying, hey, this is instant time. There's no necessary search time. Well, that's not the case because when we're utilizing Big O, we're always interpreting things by the very worst scenario, which in this case, the worst scenario would be where we were looking for the last number in the list, at which point this would turn into log of n. For linear time. Does everyone understand that?
I'm a little confused. Why wouldn't it be O of n if n is just the length of the list?
O of n, I may be having those. Oh, here you go. So I did get those confused. I apologize. So O of n would have been our worst scenario, whereas O of 1
Would be instant.
would be our instant. Yes, that's correct. Thank you, Tim, for pointing that out. I appreciate it.
Yeah, no worries.
And let me go ahead and draw that in there. There you go. So best scenario versus worst scenario. All right, it doesn't seem like there are any questions, so let's continue going into our big O notation here. So here we have a constant time, a linear time. So here's an example of a constant time. This is access an element. It's going to take in a list and an index. Well, this is just returning a specific index within that list. It's not iterating through anything, so that's a constant time. Then we have linear time, where linear time is more like our simple search. It's going to iterate through something, and at the end of it, return whether something exists or not. All right, so it looks like that's all we're going to be doing as far as a comparison for this first portion of the lecture. The next portion of the lecture, we're going to do this logarithmic practice, which is just essentially a couple of mathematical equations for us to get more acquainted with logarithms. We're not going to spend too much time on this. This is just for us to get more into, oh, okay, this is how logarithms work, and this is how the math is happening or being determined behind the scenes. And then we'll come back and continue with determining big O notation. Currently, it is 1:43. Let's go ahead and take the next 17 minutes to tackle that logarithms practice. With that said, I'm going to pause the recording here. All right. Excuse me, everyone. There you go. Welcome back. Let's go ahead and go into part 2 of our lecture for big O notation today. So now we're going to talk about determining big O notation. Now for determining big O notation, we're going to look at a couple of different algorithms to understand how big O notation works, or a couple of different examples of big O notation. We're not going to write these algorithms from scratch, but we will draw them out so we can take a look at their functionality and understand why they equivalent to the correct big O notation. So with that said, first thing I want to bring up is this nice little drawing here. And I wonder if I could zoom in a bit here. Okay, that didn't work the way I planned it to. There you go. All right, so there's our big O notation complexity chart. Maybe I could make it a little bigger here. All right. So with big O notation, best thing we can provide is either instant time or O log of n time. We have O of n time, which is just the equivalent as linear time. And then after that, we just progressively get worse. We have O n log of n. And there will be some algorithms that you work with where O n log of n are going to be the best potential outcome that you can hope for. But O of n squared, O2 of n squared, or 2 squared to the n, and then O of n to the of not n. This is those are necessarily algorithms that if you wrote them and they work, but they don't have this certain runtime, but they equate to this certain runtime, more than likely they could be refactored or reworked to where they do not achieve, where they achieve something better. O and log of n should always be the goal for your logarithmics, regardless of how hard they are. If they are easier, then you should try to aim for O log of n. All right. Does anyone have any questions regarding this chart? And keep in mind, we will dive into these algorithms here shortly.
Wait, what did you call the last one though with the exclamation mark? Is that in factorial?
Let me make sure that I know what it's called appropriately. The terminology gets me a lot of times.
Yeah, the exclamation point is a math term for factorial.
There it is. Thank you. Appreciate it.
So that's like, say n was 8, so it'll be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, basically, right?
Right. So essentially, the more input there is, the worse the algorithm will operate.
Heard.
All right. Awesome. So now let's start diving into a couple of these different functions. So we have this list of numbers and we have linear search. We already determined that linear search equates to O of n. Now there is constant time where we are looking at O of 1. What would an example of constant time be? Well, in this case, we can get a return index or return value. And what this does is it will take in X for the index we want. We'll just call it IDX to be a little bit more specific. And then a list. And what this will simply do is it will return the value at the list index. All right, so that's O of 1. What other data structure do we know of that has direct access that will always operate as O of 1?
Dictionary.
Yeah, a dictionary, right? A dictionary is a key value pair. And no matter what we do, a dictionary will always return O of 1 when we're accessing it. All right, that is also equivalent to O of 1. And that's why dictionaries are usually your preferred data structure whenever you're working within algorithms. Usually, if there's something that can be fixed with a list, it can also be fixed with a dictionary. All right. Does anyone have any questions regarding O of 1 or O of n? All right. Can anybody think of an example for O log of n?
Isn't that like binary search?
Yeah, awesome. So we have our binary search, which binary search should be something as follows. Let's see if my memory serves me correctly. Let's do binary search, which takes in a number and a list. And we establish low be equal to 0, high be equal to the length of the list minus 1. Oh. All right, and then while low is less than high, then, oh, and this should be equal to, less than or equal to high, then what we're going to do is we're going to establish middle. And what the middle should be, it should be high minus low with the floor division of 2. Because we want that index. And then we want to check if the list at middle is equal to the target, or excuse me, the number, then we simply return middle. Elif list middle is greater than the target, then we want to shift. If the list middle is greater than the target, we want to shift low. We want to shift high. We want high to be equal to mid minus 1. And then else, we want to shift low to be equal to mid plus 1. If we break out of this while loop, we want to return -1 or none because this doesn't work correctly. Now, let's draw this out. Why is this O n or O log of n? Let me go ahead and delete this information that we currently have. And let's say our targeted value is this nice little gold square here. Well, what we're going to do is we're going to determine low. We will then determine high. And from both of these, we're going to check, hey, is low still less than high? From there, we'll determine a middle. And for simplicity's sake, let's say middle is right here. All right, so it checks middle, and it says, hey, is this current value? And this is, of course, assuming that this list is sorted. Is this current value less than high? Or is this current value greater than the middle? So here's where our comparisons come in. It brings it down. It is not equal to the target, but it is greater than said target. So because it's greater than said target, we're going to reassign high to be equal to the middle. Or excuse me, to the middle minus 1. So let me go ahead and copy and paste that here. So now it's equal to that. The while loop repeats itself. So now for our next iteration, what we have is low, we have high, and then we have middle. Now in this iteration, the two that are being asked is going to be middle. Hey, is middle less than high? Because it is less than the number that we're looking for. Excuse me. It's not necessarily the fact that it's high, but it's looking for the number that we're looking for. It's going to reassign low plus 1 to be the middle. Or excuse me, it's going to reassign low to be mid plus 1. There you go. We are getting there. Finally, last two numbers that fall in here. Actually move this further down. We have our low. We have our high. Low is still less than or greater or less than or equal to high. So it falls these two into comparison. At this point, there is no middle. So the middle will fall into 0. Looking something like this. meaning that low will get reassigned to be our high number. Finally, that high number drops down. It's the only one left. And at this point, low, high, and middle, because its low is less than or equal to, will all be living inside of the same algorithm or inside of the same index. At this point, it's matched to the target. So mid is finally returned. Now, if we take a look at our little pyramid structure here as to what's going on, let me try to line that up a little bit better. You'll notice that all we essentially did was take the original list, cut it in half. We then took that list and cut it in half again. We then took this list and cut it in half one more time until we finally reached our assigned value. And that is why it is determined as O log of n, because every iteration, it cuts the number that it's looking through by half. Does anyone have any questions over this?
Morty brought up in the chat your mid should be your high plus your low divided by 2. Not
My mid should be my high.
high plus low instead of high minus low.
Yeah, line 24.
Oh, thank you so much. That makes a lot more sense. That would only work if low equals 0, low is 4.
Yeah, I was wrong. Just ignore me.
Oh, okay. Got it. Reading through.
So I guess this is O of log in like worst case scenario for a binary search.
Correct. All right. So now what are some strengths and weaknesses? All right. Because we could just do a linear search. A linear search would have worked just fine. But a binary search in this case works more efficiently as far as efficiency goes, but not as far as memory location goes. So a weakness of the binary search is that it utilizes more memory allocation. There's one. What's another huge weakness about the binary search in comparison to the linear search?
It only works on sorted lists.
Exactly. It only works on sorted or on pre-sorted lists. So whenever we're working within a database or we're working with our queries later on as we work into our full stack development and we're within the backend, grabbing information out of our backend directories, or excuse me, out of the database, more than likely we can get those query sets back in some sort of sorted format because we can sort it from our SQL query. Now, those are times that we can utilize binary search to organize things. But if we're working with something that isn't sorted, which one of these two algorithms would I want to use? Would I want to use a linear search or a binary search?
Binary. I'm sorry, linear.
Yeah, we would want to use a linear search in that case because it is not a sorted algorithm. So just keep that in mind. You could make the argument that you can always write a sorting algorithm, sort it, and then afterwards apply the binary search with yes, which yes, of course you can do that. But more than likely, if you combined the binary search plus the sorted search, you're losing a lot more in memory than you are gaining in efficiency. And of course, that's also depending on how much information you have. Because if you're interacting with a ridiculous data structure or a ridiculous amount of input, then it might be worth going through the process of sorting it and then doing your search process. But it is all a kind of, or even just mixing the two. We also have something called merge sort, and it's a whole mess. But we'll get into that later on as we keep diving into our algorithms. All right. The next thing we're going to talk about is going to be quadratic time. We are good on time to be able to talk about this. I'm not going to write this from scratch. I'm actually going to write it out or paste it so we can visualize it. So this is going to be O, and let me make sure we don't have another I apologize, everyone. I'm not going to be able to dive into linear arithmetic search with the merge sort, but we will get through bubble sort here shortly. So this one will be O of n squared, which is equivalent to quadratic time. And if we take a look at our big O chart, quadratic time falls in here, whereas the number of input rises, so does the amount of proficiency. Right? We just talked about O n log of n. We talked about O of n. Excuse me, actually, we didn't talk about O n log of n. We talked about O log of n and then O of n. Now let's dive into this O of n squared here. For this O of n squared, what we have is the bubble search function. Now, the way the bubble search function works is it takes in a list. Let me just grab this handy dandy list here. And its purpose is essentially to sort an algorithm. Now, how does it sort it? We have n, which is equal to the length of the list. For simplicity's sake, let me actually count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, we have 12 inside of this algorithm. Then it says for I in the range. So it's iterating through the first time. Then it says for j in range O of n, so this is the length, minus 1, meaning that what is being selected is this square for j. Oh, excuse me. So here's our j. And then our I is just j plus 1. Actually, I'm not seeing I being referenced to here, other than for this first iteration. All right, so in this case, we have n, which is the length of 12, minus 0, because the very first iteration is going to be 0, minus 1, which is negative 1. Excuse me, which is 11, not negative 1. So 12 minus 0 still gives me 12, minus 1 gives me 11, meaning that what I'm iterating through will be from here to here. Then I ask a question. I'm asking, hey, if array of j, which is my current location here, is greater than array of j minus 1, so we'll just call this j plus. Oh. If it's greater, then I'm simply just going to switch these two locations. So if it's not sorted, it will switch them. And that kills my first iteration. Or excuse me, it does not. Got these mixed up. This is what I'm looking through all the way up to here. I am not touching that very last index. That last index never gets touched or it doesn't get iterated through. We ask these questions. If it is, it switches it. And then a copy of this array falls through, or this list falls through. And then it repeats the same process. It goes through yet again, where now j is represented by the next index, and j plus is the one right next to it. and continues moving forward over and over again. So we were to draw this out, what it would look like, something like this. And so on. I'm going to go ahead and stop after this one. Now, why could this be a problem? Well, you see, what we're drawing out here is just the very first iteration. But this isn't only this process of sorting the algorithm or sorting the list from left to right isn't only happening once. It is happening for all 12 indexes. So this exact process that we just drew out is actually happening. Oh, hello. Another 12 separate times. And that's what turns it into a quadratic formula. It's the fact that it's not only iterating once, but for every single one of those repeated iterations, it is also being iterated through the entire list over and over again. So what we drew out was only half of one of the iterations, but that gets multiplied times the amount of input as well because of this parent for loop. Now, a very strict and straightforward signifier as to, hey, this is how do you identify if it's quadratic time. If you have a nested for loop inside of another, more than likely you're writing in O n squared time. That's just how do you put it in straightforward terms. Does anyone have any questions over O n squared?
Why do we never touch the last index?
We never touched the last index because of this portion, right? So if n is equal to 12, so you do O n minus 0, that's going to still give us 12. Minus 1 gives us 11.
Yeah, but
should-
like,
should-
why? Like, why is that important for our data? Because, like, what if J, by the time it gets all the way to the end, it never checks to see if it's greater than that last value, and what if it's not?
Yeah,
Or
it
what
should
if
just
it
be n
is?
minus I.
Yeah, the reason behind that, and I fully understand why the question is coming up, is because once it gets to the very end of the algorithm, or excuse me, of the checking process, just like you said, J would be represented by the last index, but J plus would be the very last one. So if you don't have that minus 1, what would happen is you would knock your algorithm out of index, because instead J would be here. And when it tries to access J plus 1, that would not exist within the list.
Tracking.
And that's the reason why we do the minus 1 to not touch that last index.
And what do you call this? Oh, wait, never mind. I see the name.
This is called bubble sort, yes.
And then I'm wondering if this only works with like numbers, because we're looking at like the index of that list. I guess it has to be a data type of an integer.
No, so you could do comparisons between alphabetic numbers, between alphabetic characters as well. So if we go into Python here and I say, hey, is A greater than B? You'll see that comes back as false. If I say B is greater than A, that comes back as true. All right, so same thing. We would expect Z to be greater than B. And that also comes back as true. Essentially, the further down the alphabet they are, they'll be greater than the prior number before. The only thing that you do have to take into account whenever you're working with alphabetical letters is capitalization. I would make sure that when you run that comparison, it's always in lowercase because I believe that this throws off the return value, and it didn't in this case. But I would strongly recommend watching out for capitalization. I can't think of an example at the top of my head to demonstrate it, but I know that it will get in the way. Does that answer your question?
Yes, sir.
All right. Any other questions? All right, fantastic. I apologize for not having enough time to go into merge sort, but we will have a whole day dedicated into merge sort because that is a monster of an algorithm. And even if I tried, I don't think I could explain it in an hour. At this point, this is going to conclude our Big O notation lecture. Does anyone have any questions over any of the material that we covered over Big O?
I guess a quick question. I looked ahead and I saw there was an O to the like the N times M. Is that pretty much worst case would be still be O(n) squared?
O n of log n? Is that what you're asking?
Like O and then and the exponential value would be N times M. I just saw that as an example, kind of just looking a little bit ahead, of some of the snippets.
Interesting. I'm looking at our curriculum right now, and it doesn't seem like I see that. I may have to ask you to share that with me, and that way I can answer your question. I don't want to just answer it without knowing what
Yeah.
you're referencing to.
Okay.
I think it's more of a grid, it's like a 4 by 6 grid. So it's instead of n squared, it's n times m, because you're different lengths in with loops inside loops, right?
I
So
think
that's yeah.
yeah, I'm not sure if you're trying to answer the question for me, which great if you are, I really appreciate it, but I wouldn't be able to answer that question unless I see what you guys are referencing to. I apologize.
Yeah, I'm sorry. Yeah, I'm trying to pull up an example real quick.
Awesome. Thank you. Any other questions?
Can you scroll down a little bit so I can see the full binary
Okay,
search?
I can share my screen if you can quickly answer.
Thank
Absolutely.
you. Just want a screenshot.
Oh, awesome. No problem. All right, let me go ahead and pause the recording and then you could share your screen here.
Oh.